Hello everyone, this is my final project for robotics and controls. The purpose of this project was to build a dynamic control system to allow a 3 degree of freedom arm move to a target position while balancing a frictionless object at the end. That frictionless object is this blue block right here. You could actually consider it a ball of a bulb, since it's sitting on it's on a prismatic joint with no external forces on it, no friction, nothing to stop it from moving and just sliding off. So let's run the system and see it run. While that's happening, let's give this some more space. And while that's running, I'll explain my system as a system itself. The two inputs are the desired coordinates you want the arm to end up moving towards on a Cartesian XY coordinate system, and the amount of time you want to give it to reach that position. The information is fed into a block where it would take the inverse kinematics and generate the trajectory of the system. Seems like our robot has finally reached its final destination, and it will try to reach a steady state where the block is balanced in the center. So we could just stop this and focus on the system itself. Alright, so this system, the inverse kinematics actually we use a geometric solution to solve how the configuration of our arms, or better said, the data values of our motors to reach the target position. So since we're using a geometric solution, there's more than one way to reach it. So the arm could be upside down, or it could be upright. So we have a couple of lines right here to determine which is the most similar position, similar configuration to what we have right now. So we won't be expending a bunch of energy moving to the configuration that's really different from what we are. So this kind of helps the robot be a little bit more efficient and run a little bit better. Alright, so the next is the trajectory generation. I decided to use a high order polynomial system. It's only a couple of lines due to the fact that I simplified it. The original code is a bit longer than this. This is the actual original code that I used to create, to derive those functions that ended up in the block. So MATLAB and Simulink are really big, powerful programs. So it could be a little bulky when you get too much going, since the system has to recalculate the values for each time step. So there's a big focus on optimizing the situation, optimizing the efficiency of the system. So now we have our trajectory generation. We actually move forward. We compare the desired values that we want, these values, to what's actually happening with the block system, which is this right here. This is our system where the simulation is held. These values are then compared with each other, and creates a general error for the system. That error is then placed into the manipulator dynamics of the system. The manipulator dynamics have been split up. This block right here is the mass forces that need to be accounted for. So everything is on to the first order. For data 2, data 1 for each of the motors. So these are just, if you open up the block diagram, it's actually just long strings of code, long strings of equations. Same for the other block, which accounts for forces such as centrifugal, gravitational, and Coriolis effects. So there's a little bit more going on here, but the original script used to make these equations is much more simpler. This is the actual script that I wrote to create these manipulator equations. It's really simple. It's pretty simple, but after iterations and reusing of equations, where it gets really long, I think it goes through 3 or 4 different iterations and reused 3 or 4 times. So I actually had to use 2 different computational softwares to derive this. The other software I used, besides MATLAB, was Maple. It had better visualization. And it had better functionalities that MATLAB originally didn't have, such as removing the non-zero coefficients, graphing tools, etc., etc. So after that, after the dynamic forces are calculated, we summate them and return them to the robotic arm, which is this corner right here. If you take a look inside, you can see that each joint is constrained by a revolute joint about each one. Each and we have torque being applied to each joint, and we have sensors at each one. So we have an idea of the position, and the robot is able to determine what it's actually doing itself. I also put in a small block diagram to allow us to disturb the system as it's running in time. We were able to push it forward, you can move it back. That's actually uh, okay, the system is being a little bit weird. Alright, so right now, the original simulation, we have it moving from the 4th quadrant to the 1st quadrant. So let's push it a little bit further and move it from the 4th quadrant to the 2nd quadrant. Therefore, actually touch on all of its extremes of its workspace. Right, let's change that to 14 and 20. Alright, let's run the system to see how it works. Alright. Alright. So let's enable this. So this project probably took me about a little less than a week to complete. This originally started as this is actually the 2nd revision of our project. The original was actually a 2 degree of freedom arm with its end effector constrained to the x-axis. So it was a very simple system. It ran in a single loop. Uh, so moving up to this, you can see how much more complicated it gets. It's definitely it's definitely very difficult. About half the time was spent debugging and solving issues. One of the main concerns was actually in trajectory generation, where once it goes beyond since this is a high order polynomial system, the 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 coefficient to the highest polynomial will eventually dominate the system. And since that coefficient is a negative value, it'll drive the system to a really high negative value, and you would just see this robot spinning back and forth. So that's one of the bugs. Another was in the inverse kinematics, where the original way we solved the system would actually create imaginary numbers, which would not appear if we were writing this in C or C++ or any sort of code. This only happens in MATLAB. The worst part about that, it was the system would still run, it would still reach its target destination, it would just run really slowly. It wouldn't reduce the time steps, the system would just move very slow. So it was a really confusing problem. Finding the source of that problem was really, really annoying. It wasn't recognized. It was kind of a light bulb moment when you just kind of added one and one together and it made sense. Stuff like that. So let's try to mess with our system a little, put some disturbance in it. Alright, you can tell that our robot is moving back and forth. Let's push it the other way. So you can see our third joint move accordingly to rebalance the block. And system's running smooth and nice. So I appreciate anyone who is taking the time to view this video, and thank you again. Have a good day.